And I'm live. That is cool. Today is 24th of August 2025, Sunday, and today we are going to delve into dynamic programming. And to help us through that, we will have Competitive Programmer's Handbook, which is a very nice book for competitive programming. And let's see how far we can get on our own. And this is going to be cool. Like, actually, dynamic programming is cool. I do not understand about knapsack till now. Like I know what the problem is supposed to be, but how do we get to the answer using that tabular method that they have? It is going to be fun. Not here, dynamic programming, right here. Okay, I have done coin change, which is cool, which is pretty easy actually. If you understand what the thing is and how we are finding it using memoization. So coin change is cool. Now, from the start, dynamic programming. Dynamic programming is a technique that combines the correctness of complete search and the efficiency of greedy algorithms. Now, what does that mean? Dynamic programming is the technique that combines the correctness of complete search and the efficiency of greedy algorithms. That is, if we were to like make a whole diagram, there is, okay, for your problem, let's say your problem is P, and then there is a whole set, let's call it S, and this set has a lot of solutions. Let's call them S1 and S2, S3, dot, 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 a lot of things. And there is one particular solution, let's call it Sx, that is the correct solution for your problem P. And what complete search does, it goes through every single solution, which could be the answer, and finds the one that is the answer, that is in our case this one, and returns it. So that is complete search. You are going through the complete set. And what do you do in greedy algorithms? In greedy algorithms, you see, let's say you are on a particular solution and there are some solutions before it, above it, after it, and the closeness of two solutions is the indication of how different they are or like how less different they are. So if two solutions are very close to each other, it would mean that the difference in them is very low. So whenever you are at a particular solution, you choose the one that fits best to your case locally. And the hope is, not even the hope, you have to prove formally that by making the best local choice, you will get to the most optimal global answer. And in that way, you do not have to go through the whole set of solutions. You just keep making the best choice at every moment locally, and hopefully, magically, you get to the correct answer for the whole thing. So that is cool. That is greedy search. And in dynamic programming, we combine the correctness of complete search and the efficiency of greedy algorithms. In greedy algorithms, you do not go through every single solution, so it is efficient in that way. And complete search is correct in the sense that you are going through every single thing, so it is correct. Now, dynamic programming can be applied if the problem can be divided into overlapping subproblems that can be solved independently. If you have a problem, like whatever, if you have an array and you have to do something to this array, and whatever you have to do, let's say you have to do q is some operation that you need to perform on this whole array, and what you could do is perform this q operation on smaller bits of this array, divide this whole array into smaller bits, and performing this queue operation on the whole thing would be very bad, and you would not like to do it because it would be very inefficient. It could even take it normally could take 2 power n, big O of n time, which is a lot, which is very big. So you could say that you are doing this Q operation on every single individual bits, and the condition is that to perform this Q operation on a single element of this whole array, you do not need to know anything, or you do not need to know anything or about some other part of the array. And even if you do need to know, then to perform that operation on that thing whose information you need to know, you do not depend on this. That is no circular dependency. So that is cool. There is no circular dependency in that way. There are two uses for dynamic programming. Finding an optimal solution. We want to find a solution that is as large as possible or as small as possible. That is efficiency, finding an efficient solution from the whole sample space of solutions. From the whole sample space of solutions, you are looking for the one that is the most efficient, as it might be the largest or the smallest, depending on the question. Counting the number of solutions. We want to calculate the total number of possible solutions, which is also cool, which should be the size of the set of solutions. We will first see how dynamic programming can be used to find an optimal solution, and then we will use the same idea for counting the number of solutions, which is what dynamic programming is used for finding an optimal solution or counting the number of solutions. So we will first see how to find an optimal solution, and then we will see how to count the number of solutions. Understanding dynamic programming is a milestone in every competitive programmer's career. So that is cool. I think we should focus therefore. And while the basic idea is simple, the challenge is how to apply dynamic programming to different problems. This chapter introduces a set of classic problems that are a good starting point. Okay, even though you might understand what the concept, what the model of dynamic programming is, but looking at a problem and then finding out how to divide this problem into sub problems which overlap in such a way, which do not overlap, or even if they do overlap, the data that is required to on the overlapping part can be pre-calculated. So applying dynamic programming is harder than understanding what dynamic programming is. That is one thing. And the classic coin problem. We have now the classic coin problem. Hello. Reducing time complexity. Yep. Hello, Jatin bro. How are you? I am amazing. How are you, Mr. Ethics? Yep, we have to reduce time complexity because going through all the solutions can take, like, if you have a set, if you have a set of elements, and this is very amazing. If you have a set of elements, let's say from x1 and x2, x3 and x4. Let's say you have four elements in your set. Now, how many subsets can you make? For every element, you have a choice either to take it in your subset or not. Therefore, for this element, there are two possibilities. For this element, there are two possibilities. For this element, there are two possibilities. Either you take it or you don't take it. So in total, there will be, and the size of the set is 4. So 4 or 2 power 4, that is 16. There are 16 possible subsets for this simple set, which only has 4 elements. And if your sample size is 10 to the power 6, you will be in a bit of trouble if you were to go through every subset permutation. So yeah, you should not do that. You should instead go with dynamic programming. Like, just look at this number, 2 power 10 to the power 6. That is 2 multiplied by itself a million times, 10 to the power 6. That is a crazy number. Is it larger than the number of atoms in the universe? No, no, it cannot be larger. Number of atoms in the universe. Okay, it is very, wait, it might be actually larger than that. Base 2, shit, shit. There are 2 to the power 266 atoms in the universe. 2 to the power 266 atoms in the universe, and our possible sample space for a set with a million items is of size 2 power 1 million. So this is much bigger than that thing. Yeah, we cannot go through every single thing, even if we had a supercomputer which has the computing power of all the matter in the whole universe. That would not make sense, right? This number is way too big. Now, coin problem. That is what we are going to get at. We first focus on a problem that we have already seen in chapter 6. In this is chapter number 7. Chapter number 6 was on greedy algorithm. So, given a set of coins, these are the denominations C1, C2 till Ck, and a target sum of n. Our task is to form the sum n using as few coins as possible. We want the sum of the coins that we are choosing to be equal to n, but the number of coins that we are choosing, we want it to be as small as possible. In chapter 6, we solved this problem using a greedy algorithm that always chooses the largest possible coin. The greedy algorithm works, for example, when the coins are euro coins, but in the general case, the greedy algorithm does not necessarily produce an optimal solution. And what does that mean? If your coins are like this, like you might normally see 10, and you want to get to a sum of, let's say, 37. In this case, you choose the biggest number, 10. Now your target sum is 27. Now again, you choose the biggest number, 10 possible. Now your sum is 17 that you need. You choose the biggest number. Now your remaining sum is 7. Now the biggest, you cannot choose 10 anymore. You have to choose the smallest, the second biggest number, which is going to be 5 plus 5. Now the remaining sum is 2. You choose 2. And this thing is going to be the optimal answer to get to a sum of 37 using the smallest number of coins, because you cannot do this any better. And that is only true in this case. But if you had something like, if your coins were like 1, 3, and 4, and your target was, let's say, 7, not 7. If your target was 6, yep, if your target was 6, then using a greedy algorithm, you would choose 4. Now your target is 2. You cannot choose 4, you cannot choose 3, you would have to choose 1. So you choose 1, now your target is 1. Now you again can choose 1, and this would be the solution given to you by our greedy algorithm. But instead of this, using these 3 coins, 4, 1, and 1, you could have gotten to 6 using 3 coins. 3 plus 3, that is 6, and these are only 2 coins. 2 is smaller than 3. So this is cool. So greedy algorithm is giving you a wrong answer. And there is a thing why greedy algorithm works in this kind of denomination of coins and not here. It is because in this thing, if you see 10, if you are using 10, then there is no point in using anything. If you have the option to use 10, you should always use 10, because other way to achieve a sum of 10 would be using 2 5s. So that is bad. Here you are using 2 coins, but you could have used a single 10 coin to represent that same sum. And same goes for 5. If you have the option to use 5, you would not like to use anything smaller than 5, like 2, because if you were to use anything smaller than 5, you would have to use something like this, which is 3 coins, and you could have used a single 5 coin instead. And same goes for 2. Is you If you have the option to choose a 2, you should choose a 2, because anything smaller than 2 would take more than 2 coins, more than 1 coin to get to a sum of 2. So that is bad. And how does that reflect in our case here? I think here we have more refined thing. Here you could choose 7. You can just directly choose this thing. And if you were to, yeah, 7 is not a good example. 6 is a good example. If you have the option to choose 4, you should choose 4. No, you could choose something better. You could choose 3. Yeah, there is some mathematics. There is some mathematics at play here, which you could use. I am good reading same book along with you. That is cool. This is the book, right? If I can go through this book a couple of times by the end of this year, it will be really cool. Now, coin problem. And the thing that I did with number theory chapter was very cool. I would not have been able to go through the whole thing on my own in as much comprehensive clarity as I did on stream. So that is what I'm going to do from now on. If there is some chapter that I want to go through, just stream about it. And today is also a contest. We will see how that goes. Now, coin problem. Yep, in chapter 6, we solved the problem using a greedy algorithm that always chooses the largest possible coin. The greedy algorithm works, for example, when the coins are euro coins, but in general case, the greedy algorithm does not necessarily produce an optimal solution. We just proved that. Now is the time to solve the problem efficiently using dynamic programming so that the algorithm works for any coin set. Does not matter what our coins are, our algorithm should work. The dynamic programming algorithm is based on a recursive function that goes through all possible possibilities how to form the sum, like a brute force algorithm. However, the dynamic programming algorithm is efficient because it uses memoization, not memorization, it is memoization, and calculates the answer to each subproblem once. We do not repeat things, so that is cool. Recursive formulation. The idea in dynamic programming is to formulate the problem recursively so that the solution to the problem can be calculated from solutions to smaller subproblems. In the coin problem, a natural recursive problem is as follows. What is the smallest number of coins required to form a sum X? Yes, we were looking for what is the smallest number of coins required to form the given sum n, but now we have generalized it for any sum x. And let solve x denote the minimum number of coins required for a sum x. The values of the function depend on the values of the coins. The values of the function depends on the values of the coins. Like it does matter on the domination of the coins. And this is the example that we used. It matters on the domination of the coins that have been given to us. What would be the smallest number of coins possible to get to a certain sum? And for example, solve 10 to get to a sum of 10 equals 3 because at least 3 coins are needed. In this case, we, uh, yep, we can choose 4 and then 3 plus 3. That would be equal to 10. Yep, 4, 3, 3, 10. The essential property of solve is that its values can be recursively calculated from its smaller values. The idea is to focus on the first coin that we choose for the sum. For example, in the above scenario, the first coin can be either 1, 3, or 4 in this, right? 1, 3, or 4. If we first choose coin 1, the remaining task is to form the sum 9. That makes a lot of sense using the minimum sum number coins, which is a subproblem of the original problem. Yes, if we have already made one choice, what would be the best possible solution for the same problem if our input was 9 instead of being 10? Of course, the same applies to 3 and 4, in which case, in 3's case, you would have to solve this, solve 7, and in 4's case, you would have to solve this, solve 6. Thus, we can use the following recursive formula to calculate the minimum number of coins. This thing, right? Because that is the only number of possible things you could use, right? Either you use either the last coin that you use, or you could say the first coin that you use. If it could be a one coin, a coin which has a value of 1, it could be a coin which has a value of 3, or it could be a coin which has a value of 4. Those are the only possible values. So you find the answer to get to a sum of x minus 1, that however amount of coin it requires, that plus one coin for this one coin, and you do this for all the possible denominations, and whichever returns the minimum number of coins, that would be your answer to solve x. And then when you are solving for x minus 1, you can do the same thing there. The base case of the recursion is solve 0 equals 0, because to get to a sum of 0, you use 0 coins. You do not use any coin to get to a sum of 0. If you do not have any coins, you do not have any money. You are poor, because no coins are needed for an empty sum, right? Now, solve this is equal to solve 7 plus 1 if you are using coin 3, which is okay, because in this case, if this is the denomination of coins we are using, this thing would be equal to, let's say you chose 3 as the first coin, then you need to get to a sum of 7 plus 1 1 for this 3 coin with value of 3. Then you chose your third coin, second coin with the value of 3, which gives you a remaining sum of 4, and you have chosen two coins till now, both with the value 3. Now you can choose a single coin of value 4, which gives you have to solve for 3 and for 0, and answer is, and 3 for the number of coins that you have chosen till now equals 3. Now we are ready to give a general recursive formula that calculates the minimum number of coins needed to form a sum x, and this is also very intuitive. Well, if your x is lower than 0, then what do you even do? Like, what do you even do? How to get a sum of negative? How to be in depth and not depth? How to be in debt? Debt. Yeah. How to owe people money? And if it is 0, if you want to get to a sum of 0, then you do not use any coins. But if you do this, then you one by one iterate through all the coins. This thing. C, go through or the go through the set of coins. Coins contains all the possible denominations of coins that you could use. Solve it for every possible coin, add one, and C, find the minimum value of among them. That would be your answer. First, if x less than 0, then the value is infinity, because it is impossible to form a negative sum of money using positive integer coins. Then if x equals 0, the value is 0, because no coins are needed to form an empty sum. Finally, if it is greater than 0, the value c goes through all possibilities how to choose the first coin of the sum. And we are not going to look at the solution, we are going to write the solution. Let me restart my tmux. Tmux set. Okay, I have to kill the server before. That is the wrong command. Tmux kill server, tmux set, and tmux attach, and the target is BSA, we could say. Go to concept, go to DP, and there is the rod cutting problem. We are not doing rod cutting, we are doing point.cpp. And okay, our function integer, its name. Shit. Naming a function is harder than writing a function. Let's call it min amount coins, and this is going to take a vector of integers which represents the coins and in sum. Now we do not have anything named vector, so we will include std bits std c++.h, and of course using name space std. And here we are going to iterate Okay, first we will have our base case. Yep, we will have our base case if if not sum, return 0. If not sum, then return 0. Int res equals int max, return res, and now we are going to iterate through all the possible coins, and if sum, that is the sum that we need, minus x, if that is greater than or equal to 0, we will see res equals minimum of min amt coins. Call this function with coins, and the target sum we need is x minus, oh shit, we have to pass the target sum inside our min amt coins function, minimum amount of coins function. It is going to be sum minus x comma response. Find the minimum value, and we should be done, except the fact that this is very unoptimal because of this. Now it is very, very cool. And actually, this is recursive. We could have used an iterative method, which we are going to use after this. And yeah, this should be cool. And main, let's say sum something, cn, get the number into sum, and our vector of coins is going to be, let's say, 1, 3, 4, the same thing that was given to us in the book. And now see out the minimum amount of coins required. Shit, why does this thing not have a name? Coins, and our sum is this thing. Okay, and cool. That is very cool. And concepts, lang plus plus coin, shit. Okay, cd dp and dp lang plus plus coin and out. Okay, for 10, our answer here was 3. Let's see. 0 makes total sense. Of course, shit. Shit, shit, shit. We messed up here. We messed up here. We messed up here. +1. +1. Yep, we messed up. But now it is cool. Now it is cool. 10, 3. That is cool. We can check this for every other thing that was given to us. And I would like to do some testing. If we have a very big number, let's say like this, segmentation fault, because that might be too. Let's make this long, and yep, that is cool. And this is also going long. No, this is going to return an integer. Integer is fine. And this is also long, so that is cool. But was that the mistake? We had, how many digits are we having? 1, 2, 3. This is not a lot of digits, so this should have been fine. See, it is taking a lot of time. It is taking a lot of time because we do not have memoization, and we are going to fix it. See, it is still not working. And we are going to fix this thing by using a thing called memoization. Map from integers to integers, and we can change the thing back actually. Change this back to an integer and change this back to an integer, and here we are going to call this thing memo. Memo is what we call it, and if memo for sum, If we already have the answer, then return memo sum memorization. And before returning, if we didn't have it, then we would do memo sum equals rest response. Now this should be much faster, hopefully. 1, 2, 3, 4, 5. This is actually much faster. 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe we went a little out of the range. 7. Okay, that seems to be too big. 6. So that is cool. We are getting the right answer. But when sum is big, it seems like our answer is wrong, but it shouldn't have been. Uh-huh. Define int as long. This should certainly, okay. Int 32. Yeah. Now this should work. 1, 2, 3, 4, 5, 6, 7, 8. Segmentation fault. Why would you see a segmentation fault at something like this? Some, not some. Return 0. Segmentation fault actually does not make any sense. I'm not segmenting into anything. Segmentation fault. My integer size is not very big. The numbers that we are using is not very big. Segmentation fault, and we are only segmenting into something like this. Memo. It might be because this thing is calling a lot of recursive functions. Yes, yes. It might be because stack stack overflow. Shit, this might be a stack overflow actually. Segmentation fault. This might actually be a stack overflow. That is how you solve coin change. This book is Competitive Programmer's Handbook. The thing. Competitive Programmer's Handbook by, I could never remember this guy's name. Anti-Larksonen. Anti-Larksonen. Like antimatter. So that is cool. And is that the thing? If okay, we are not handling this case with school. And we do this. Yep, this is the exact same thing. Best infinity, return infinity. We have we shit. We have in shit. We have infinity. That is cool. Shit, we actually do have infinity, which is cool. We can do this because if this thing returns a very big number, we do not have to choose it. We are going to choose our res. So we do not have to see if it is smaller, and this should still work, or maybe not. Is it calling a lot of recursive calls? Okay, shit, that is messed up. This thing is actually calling a lot of recursive calls, which is bad. No, no, shit. Okay, this is actually bad. This should not be the thing. Okay, this makes sense. Shit. Okay, this makes sense. If sum lower than 0, return infinity. Clang dot slash out 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, we are getting some answer. Okay, it does work fine for smaller things, but it is not very efficient for bigger things because this is using recursion. We could instead use iteration, min amt coin iteration, which will also take in the vector representing points and an integer sum. And instead of something like that, we would have a vector of integers from, we can call this memo, and this will have no conflict with the memo that we have outside because this is inside this scope. Their scopes are different, and whenever we access memo in this scope after the declaration of this particular memo, we will get this memo. So sum plus 1 for int I equals 0, I less than or even equal to sum I plus plus. And this is what we are going to do. We will have memo 0, that is to get to a sum of 0, we have 0, and then we will start at 1, and we will iterate for int x into points, and if I minus x greater than 0, greater than or even equal to 0, we will see. Before going, memo I equals infinity, we could say, and if this is the case, then memo I equals minimum of memo I comma, that is the value that currently is, plus comma memo I minus x, that is because x is the one that we are using, plus 1, and we have changed the thing, and at the end see out memo sum, not see out return, memo sum, not sum, return the sum, and that is cool. This should be much faster than the thing that we were using, iterator. Okay, so here we were getting segmentation fault for a number like this. Let's try to use the same number here. We are getting answer. That is cool. 1, 2, 3, 4, 5, 6. Let's use a bigger number. We are still getting an answer. See, we are getting an answer. This is cool because earlier we were using a recursive call and our stack was getting filled because of the recursive calls, and in turn causing a segmentation fault, but that is not happening anymore. Now we are not making any strange recursive calls. Now we are actually doing something, so that is cool. Now we are simply using a loop starting from 1 till the sum, and then at the end we are outputting the sum, so that is cool. And if you want to understand this coin problem, I would highly recommend watching Erkto's video on this thing. Erkto DEP, dynamic programming. Yep. These two, I think he has 3 videos on dynamic programming. Yep, dynamic programming 3. These videos are pretty good. Still, this function is not efficient because there may be an exponential number of ways to construct the sum. However, next we will see how to make the function efficient using a technique called memoization. That is what we did. First, we used this function barely without memoization, without this thing. And then we used this thing, memoization. So first, bare recursion, then recursion with memoization. This is not memorization, and then iteration. So this is bad, less bad, and best. So, yep, using memoization. No, this is not memorization. The idea of dynamic programming is to use memoization to efficiently calculate values of recursive functions. This means that the values of the functions are stored in an array after calculating them. Yes, when you have solved a subproblem, you would not want to solve the same subproblem again and again. So that is cool. For each parameter, the value of the function is calculated recursively only once, and after this, the value can be directly retrieved from the array in which you are storing answers for subproblems. If you have already solved a subproblem, you would not want to solve the same subproblem again, because solving one subproblem is going to cause recursive calls to even smaller subproblems, and you do not want that. In this problem, we use two arrays, ready and value. Uh, I think you didn't have to use this. You could have just used this array, which would have been better, because you can initialize everything in this to some value. Let's say my, wait, shit, am I stupid? Actually, I am. Shit. No, 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 no. It is fine. It is fine. It is fine. I'm not stupid. It is fine. Yep, this is fine. Now the function can be implemented efficiently if we are using two arrays. One will tell us if a given number n is ready or not, if we have already solved that subproblem. And if we have, then we can go to the value subarray and find the solution for that. And instead of calculating the whole thing again, that is cool. The constant n can be chosen so that all requirement values fit in the arrays. Yep. And then we can just choose the last one. Now the function can be efficiently implemented as this. If x is lower than 0, then output infinity. That is one of our base case. The other one is this. If it is 0, return 0. And the third one is this. If it is not negative and if it is not 0 and we have already found its value, then return the value that we already found. Otherwise, best case is infinity, and then we will iterate through the points, call the function again for a smaller subproblem, find its value, update our best, and at the end, update our value, update our ready array, and then return the best solution. That is cool. The function handles the base cases, which is when x is negative and x equals 0 as previously. Then the function checks from ready x if solve x has already been stored, and if we have already found the value for our x that we are trying to find now, then we would not like to calculate the thing again, right? And if it is, the function directly returns it. Otherwise, the function calculates the value of x recursively and stores its value in value x, and also updates the ready q or array vector, ready vector. And here they are using bare C-type arrays, which is not very recommended by the man who created C++, Bjarne Stroustrup. This function works efficiently because the answer for each parameter x is calculated recursively only once because of memoization. After a value of solve x has been stored in value x, it can be efficiently retrieved whenever the function will be called again with the parameter x, because that is what we are checking for right here. If it is ready, then return it. Do not calculate the whole thing again. So we are cutting down our time, which is cool. After a value of x of solve x has been restored, has been stored. Yep. Retrieve it. The time complexity of the algorithm is nk, where k is the number of coins and n is the value for which you need to find the most efficient number of coins, where n is the target sum and k is the number of coins. Note that we can also iteratively construct the array value using a loop that simply calculates all the values of solve for parameters 0 to n. Yes, let's say we have created our value array initial for 0, it is 0, and then you start iterating from x equal to 1 till the answer. And initially for every x you start with infinity and then you loop through all the coins, and if this thing, the target sum after you use coin whose denomination value is c, if that thing is greater than or equal to 0, you update your current value x with either whatever the value was till now. In the first case, it would be infinity, or the value that you would get after using the coin C to get to this sum. You update it and it just updates. At the end, you will output a value sum or value n. N is the target sum. In fact, most competitive programmers prefer this implementation because it is shorter and has slower constant factors. Slower constant factors because we only have a single loop. We do not have any expensive recursion. Recursion is easier to imagine and easier to implement, but it is very slow. Iteration is a bit harder to imagine and a bit harder to implement, but it is very efficient. So that is what we are going with. From now on, we also use iterative implementations in our solutions. Still, it is often easier to think about dynamic programming problems solutions in terms of recursive functions. So you can build a mental model using the recursive functions and then implement them iteratively, which is cool. And now constructing a solution, which is cool. Hello, are you doing problem sets or only learning DP in this stream? We are only learning DP in this stream because DP is very big, right? I want to, at least the target is, well, we will do this thing. At least the target is to get to knapsack and understand knapsack, because I also do not understand knapsack. I understand the problem, what it is, but they use some kinds of table magic to get to the solution. And okay, so we would have to go through knapsack thing, how to work that out. And before that, this thing is cool. Paths in a grid, finding the maximum or the smallest path, which is cool. And then longest increasing subsequence, we can use Cardin. We cannot use Cardin's algorithm. Yes, longest increasing subsequence is cool. It's cool. We can do that. We will do that when we get to it. And right now we are at constructing a solution. Okay. Sometimes we are asked both to find the value of an optimal solution and to give an example how such a solution can be constructed. Okay, so you now know you need to find the solution itself, in which case you could store, in which case you can take an array. Let's say till this point you had an array which was like this, and let's say your n equals 5 and the coins that you have are 1, 3 and 4, let's say. Then you can divide this into 6 sections. Yep, I did say 6 for 0, 1, 2, 3, 4, 5. And the optimal way to get to a sum of 0 is using 0 coins. To get to a sum of 1, you use 1 coin of 1. To get to a sum of 2, you have to use 2 coins, both of value 1. To get to a sum of 3, you can get there directly using a coin of value 3. To get to a 4, the same thing. You use a single coin, and to get to a 5 you use a single coin. You use 4 and 1. This is what we were storing till now, but now we also need to know how to get to a sum of 5. We need to know that 1 plus 4 equals 5. Therefore we can store another array. We have to create another array of the same size. of the same size with the same indices. Of course, the same indices. Indices won't change if the size is same. 4, 5. And in every ith thing, you would store the value of the coin which gave you the optimal result. That is here when we were iterating C through coins, whichever coin gave the minimal value, we are going to store that coin in this array for every individual I. For example, for 0, we didn't use any coin, so you could say like 0, right? We used a coin of value 0. For 1, we used the coin with the value of 1. 1. To get to 2, we used a coin of value 1, and then our target sum became 1. And to get to 1, we choose a coin of value 1. So here comes 1. And to get to 3, we iterated through 1, and 3 and 4. If we had used 1, it would have been bad, right? We would have to use 3 coins in that case, which is not very optimal. But if we were using a coin of value 3, we could have gotten to 3 directly. So the last coin that we used would be 3. Same here, 4. And in case of 5, we would iterate through 1, 3, and 4. When we used a coin of value 1, our target sum became 5 minus 1, that is 4. And to get to a value of 4, we would have to use 1 coin. So therefore, in total, if we are using a coin of 1, we would have to use 2 coins, which would be better than the initial answer that we begin with, which is infinity. So we can store 1 here, and then we would see 3. If we were to use 3, then our target sum would be 2, and to get to 2, we would have to use 2 coins, and therefore the number of coins we would be using is 3, but it is higher than the number of coins that we already have. So we will not update anything here. Then we would use 4, and even here the number of coins required to get to to get to 5 would be 4, which would be 2, and it is not smaller than 1, so we would keep this as 1. And now this is cool. And now if we want to find the solution to get to 5, we say we first used 1. So 1 is one of the numbers that we will be using. And then our target sum became 4. What is the number that we used to get to 4? We used 4, right? What is our target number now after 4 minus 1? It is 0. Our search is done. So that is our solution. 1 plus 4 equals 5, which is cool. Now constructing a solution. First, yeah, we could call it anything. First or last, does not matter. The idea is that you are having one of the coins which you used in a separate array. The size of the things that your memory consumption has doubled in this case when you need to find a solution. Sometimes we are asked to find the solution, the value. Yeah. Then we can modify the algorithm as follows. If this thing is greater than or equal to 0, then find its value plus 1. If we used this current coin, if the number of coins would is lower, if we were to use this current C coin, then the coin that we have been using, then update value and update first. And at the end, we can just we can construct the thing. Yep, we can output this like this. Yep. Take the coin to get to n, subtract that value from n, and keep doing this till n is greater than 0. And we can do this. Int, no, this will not return an integer, this will return a vector of integers. Find solutions. It will take in a vector of integer references called coins and integer sum and vector int memo sum plus 1 and vector int, we can call this last or does not matter. And let's say here we could have used 1 plus 4 to get to 5, or we could have used 4 plus 1 to get to 5, and these two are different. Let's say whatever our solution is, we will present that solution in lexicographical order. So if we have two representations like this, we would prefer this one, where the smaller number is used first and then the larger number. And the size of this thing would also be sum plus 1. And initially everything is 0. Yep. And now for int I equals 1, I less than n less than equal to sum I plus, and if is nothing, if is nothing for this thing. Yep. For int x n points, if I minus x greater than equal to 0, and we can go back. Yep, and the answer that we will get for going back would be memo I minus x plus 1. That is the answer we would get if we were to use this x coin. If this thing is lower than the answer that we already have, which is memo I. If that is the thing, then update memo I to be equal to memo I minus x plus 1, and also update last. Last would be equal to x, on last I would be equal to x. But there is a problem. We didn't initialize our memo I. Memo I is going to be infinity, which is crazy that you can just use infinity in a programming language. Then at the end, we would have to construct our solution, which is going to be vector int response. And what is going to be the size of this thing? The size of this thing is going to be memo sum. And now, while sum, or a better coding practice would be to not change the variable that has been given to you. You might need it later. So for int I equals 0, or yeah, you can change this. It is simply an integer. While sum is something, what we will do is, or we do need I. We do need I. Okay, we will not be able to present this in lexicographical order. Yep, we will not be able to present this in lexicographical order, but that does not matter. It is fine. Int I equals 0, I less than memo sum and I plus plus res I would be equal to last for I, and I becomes greater, which is crazy, sum last for sum, and sum minus equals last sum. Return res. Will this work? This should work. We are starting with our sum. Whatever the last thing is, we are putting it equal to res I, and then we move on to decrement our sum, which with whatever the value was at that, whichever the last sum coin was to get to this sum, and that should be cool. And now here to print our array, we can use this thing which just came here magically because of the remaps. Vim remaps. Vim is cool. Vim is cool. And you can call that function find solutions. Find solutions. point, and this should work. Clang. For 10, you use 000. That is the answer. Shit. That is not the answer. Last equals x. Due to some reason, x belongs to the set coin. And if this thing is greater, then last I would equal to I, which makes sense. But why is the thing like that? We can go and compile again, and let's see. For 10, it is seems to be very, very horrible. Last output last sum plus 1, that is the size for last. What is this? ABI application binary interface terminating due to uncaught exception of type standard length error of a vector. I am going too far ahead at some point. Maybe in this case, when I'm doing this, memo sum is the number of coins required to get to a sum of this, right? Because sum is changing. Shit, that makes a lot of sense. Res dot side. And 10 answer is, yeah, we outputted this thing, which shouldn't be there when our input is 10. Okay, okay, shit. Something bad happened due to some reason. Okay, now again the same problem due to some reason. Memo sum, and I am not changing the sum at any point, so this should be cool. But I'm changing the sum here, which is also cool. And I would indeed need memo some amount of coins to get to my answer. Or I could simply use a pushback notation. While sum, what you do is rest dot pushback last thing in sum. Last thing and sum minus equals last sum. While sum, we will keep doing that. Clang compile 10 334. Cool. Something like this, you use a lot of force and two threes, which is cool. What if we have something a bit more complicated than this? Let's say 7. 7 is also justifiable. And for 6, you could choose two threes. For 4, you could, for 5, you would have to choose a 3. For 5, you could choose a 1 and a 4, which would be the correct answer. Yeah, this is cool. This is working. This is working. Yep, we have a nice solution. Produce CSCS problems, they map to this book. Yep, CSCS is also pretty cool. I've done a few problems in CSCS, only in graph, and I was just unable to do this one. Monsters. I did a lot of submissions on this, and in the last one, I was only getting one. Yeah, in second last one, I was only getting one wrong answer, which is, yeah, shit. Yeah, my algorithm doesn't seem to be very cool at this. And now moving forward to counting the number of solutions. which is cool. But here, how do we see this? Something like this. 1 plus 1 plus 3 is one solution, and 1 plus 3 plus 1 is also another solution. Do we see these 1 plus 4 and 4 plus 1 as different solutions, or do we count them as a single solution? Are we looking for permutations? So, yeah. Let's now consider another version of the coin problem where our task is to calculate the total number of ways to produce a sum x using the coins. For example, if coins equals this thing and x equals 5, there is a total of 6 ways. Here we are considering 1 plus 4 different from 4 plus 1. We are taking permutations. Again, we can solve the problem recursively. Let's solve x. So how would you do this? You would say if you choose the coin 1, how many number of ways are there to get to a sum of 4? And when you choose 3, how many number of ways are there to get to a sum of 3? And if you choose 4, how many ways are there to get to a sum of 1? And again, we can solve the problem recursively like this. Yep, add all of the ways together. That would be the answer. Then generate the recursive function as follows. If 0, then if x lower than 0, then there is no way. If x equals to 0, there is only one way in which you are not choosing any coins, which is a empty set. And if greater than 0, then iterate through all the coins, solve the same function for all of them, and output the answer. Coin problem, coin count.cpp. Include bits std c++, yes, std c++, and using using a using namespace std, and we are going to write our function find ways, which takes in a vector of integers called coins and integer n, which is going to be our sum, and rest equals initially 0, and then also there is going to be our base conditions. If n lower than 0, then return 0, and if n equals 0, which is like if not n, then return 1, because there is only one way. Otherwise, result is going to be initially 0. And for int x belonging to coins, we will iterate, and initially our response is 1, and response plus equals solve the same thing for vector for coins and for what is the sum. And the current sum would be n minus x, and at the end return rest. And this is inefficient due to a few things. First of all, we can change our vector to a reference vector, which is much better than copying pasting a vector every time. And here, this is fine, this is fine. I would like to see, to check this condition. I think we can do something much more elegant, not elegant, but crazy than this. Let's say we have n and we write shift n 31 times. Yep, we write shift n 31 times and take its and with 1. That would indicate if n is negative or not. Because after right shifting n 31 times, if n is an integer, which we are supposing it is, right here, n is an integer, then the MSB, the highest bit to, if n is an integer, then it is going to use 32 bits. This is the 32nd bit. If we are calling this one bit number 1, then this is the 32nd bit. And by doing n right shift 31 times, we have whatever the bit was here, 0 or 1, we have it here in the first place. And we are taking its and with 1. So if this bit was 0, we would get 0. And if this bit was 1, we would get a 1. 1 and 1 is a 1. And why is that something that we need to care about? Because if this 32nd bit is 0, then this whole number is positive, and if it is 1, then this whole number is negative. Why that is so? That is because of 2's complement. 2's complement, that is one way to represent binary numbers as negative numbers. That is cool. Because this first bit is sign bit. To represent a negative number, we put it equal to 1, and to represent a positive number, we put it equal to 0. So this should tell us if n is negative or not. And this seems to be correct now. Int main, int n, c in n, and vector of points is going to be 1, 3, and 4, the same thing that was given to us. And now C out, find ways using coin to get to a sum of n, and also a new line just to be safe. That is the wrong function. Coin count is the one. C out for 5, we had the answer equal to 6. We had the answer equal to 6 ways. Let's stop this and actually make these two similar. Space ways. Now we should see 6 ways. 6 ways, which is pretty cool actually. 6 ways is cool, and we have implemented this thing essentially. Okay, shit, iteration. Shit, this is bad. This is bad. This is using recursion. But we are good competitive programmers, so we are going to use iteration. Recursion is bad. Do not use recursion. Recursion is bad. Okay, so we can create a vector of res is like response n plus 1, that is going to be our size, and res is 0 to represent a sum of 0. There is only one way to represent a sum of 0. And then we can start iterating from I equals 1 till I less than equal to n and I plus plus. And for a given sum, we can do, it is well already 0. So for int x, 2 coins, if if I minus x greater than 0, or we can use the same crazy notation that we used earlier. If x, we would need something like this. If I minus x, we right shift this thing 31 times and take its AND with 1. If it is, then it would be negative. So we take its shit. Then we take its AND. Shit. Yep. We take this whole things and go there and paste. And this is way more complicated than it needs to be, but this looks cool. If not negative, then res plus res I plus equals res I minus x. That is cool enough. And then at the end, not C out, return res n. The response for n, and we should get the same output now when using 5, 6 ways. So that is cool. And this is much better than the recursive approach, which we implemented first. And now moving on. Often the number of solutions is so large that it is not possible. It is not required to calculate the exact number, but it is enough to give the answer modulo m, where m, we have done a lot of things with modulo. So we are very familiar with modulo. In the number theory video, we did a lot of things with modulo. Modulo m, where, for example, m equals 10 power 9 plus 7. And 10 power 9 plus 7 is a very big number. As you can see, it is 1 billion, but it is also prime, which is pretty cool. This can be done by changing the code so that all calculations are done modulo m. That is whatever calculations we are doing, like right here, we could change this whole thing to this thing plus res I and mod some number mod, and that number could be 1e9 plus 7. What is the error here? Invalid operands to binary conversion. We can convert this number into integer, and that is cool. This thing after the line, yeah, you could put it after the line. Now we have discussed all the basic ideas of dynamic programming. That is finding the most optimal solution and finding the number of solutions, and dividing the subproblem either using recursion or using iteration, and using memoization. And iteration is the one that good competitive programmers go with. Since dynamic programming can be discussed in many different situations, we will now go through a set of problems that show further examples about the possibilities of dynamic programming. One of them being the longest increasing subsequence. That is what we are going to do now. And what is this thing? Our first problem is to find the longest increasing subsequence in an array of n elements. This is a maximum length sequence of array elements that goes from left to right, and each element in the sequence is larger than the previous element. For example, in this thing, if we have given, if we have been given something like this, then we have something like this, and our task is to find the longest increasing subsequence. What is longest increasing subsequence? A subsequence of any string is, of any vector or any array, is one thing that you get after removing a bunch of these elements or no elements at all. You could say you are removing all of these numbers, and what you are left with would be one of the subsequences. This is one of the subsequence of this thing. So when you remove a bunch of numbers, or maybe not remove a bunch of numbers, what you get is a subsequence. Now we want a subsequence which is increasing. That would be, if we were to take 6, 7, 8, that is a subsequence of this thing. If you remove these three elements and remove this one and this one, what you're left with is 6, 7, and 8. This is a subsequence, and this is increasing, strictly increasing. Longest increasing subsequence, increasing. So this subsequence is increasing. So you need a subsequence that is increasing. But there is another term, longest. We know what a subsequence is. We know what increasing is. Now, among all the possible subsequences which are increasing, we need the one that is the longest, which in our case would be simply 2 if we take this 2, 5 if we take this 5, 7 when we take this 7, and 8. The length of this subsequence is 4, and this is the longest subsequence that is increasing. And that is what we are finding here. So that is cool. And without looking at the next thing, we can actually write this. And what we have to do is ask ourselves few questions. Take this thing, right? Remove this thing. What it is, remove it. And we have something like this. And we can change its color. But more importantly, what we know is that among all the elements that are to the left of a given number, there are only a few with which I could pair this up with. That is, if I am choosing 8 as the end of my subsequence, I could only pair up 8 with 7, with 4, with 1, with 5, with 2, with 6. I could pair up 8 with every number. So that is not very cool. But we could pair up if we were to choose something like 4, yeah, extra, just if we need it at any point. If we are going with 4, we cannot pair up 4 with 7 because 7 is greater. We could pair up 4 with 1, that is cool, but we cannot pair it up with 5, it is greater. We could pair it up with 2. And then our sub problem is this: if I pair up 4 with this 1, and what are the possible numbers with which this one could be paired up with on the left, and the subsequence, what is the greatest length of the subsequence whose last element is this one, and find that, and find the same thing for 2, and see whichever is greater, make that the answer for 4. So what we are essentially asking, okay, this is now required. Yep, copy paste this thing. We will start iterating from the first element, and we will see we cannot go to the left. So the at every point that we are at, we would see what would be the longest length of the subsequence if this number were to be the last number in that subsequence. In this case, when we are at 6, if 6 is the last number in our increasing subsequence, we cannot go any further to the left. So our answer for 6 would be 1. 6 is the only element. If we were to choose 2 as the end of our increasing subsequence, we cannot go to the left. We cannot pair up 2 with 6. So answer again would be 1. If we go with 5 as the end of our longest increasing subsequence, on the left we could only pair up 5 with 2. We cannot pair it up with anything else. And if we were to choose 2 as the end, the answer would be 1. And now we are also adding 5 to it. So for 5, the longest length of the maximum, the length of the longest increasing subsequence with 5 as the end element would be 2. Now, if we were to move on to 1, we cannot pair up 1 with any number on the left, so the length would be 1. Now, if we move on to 7, if we are choosing 7 as the last number in our longest increasing subsequence, on the left, I can pair up 7 with 1. I could pair up 7 with 5, with 2, or with 6. And among these, I can pair 7 up with all of these. Among these, the longest subsequence that I get is with 5. So that is what we are going to go with in case of 7. So 7 is one element, and the longest subsequence for 5 is 2. So in total, the longest increasing subsequence with 7 as the last element is going to be of size 3. That is cool. Now we move on to 4. We could pair up 4 with a few elements. We can pair up 4 with 1 and with 2. And if we were to pair it up with 2, we would get 1 as the longest length. And if we were to pair it up with 1, so 1 is what we would get. So we do not need to be can just choose anyone and we would get 2 as the answer here. Then we can go up to 8, and 8 we can pair it up with any number to the left. So we have to find the number which has the longest subsequence, which in this case is 7, which has 3 elements in its longest subsequence. We would take those 3 elements and add 8 to the end of them. Our answer for 8 becomes 4, and then lastly we go to 3. We can pair up 3 with 2 with 1, and they both have values of 1. So for 3 we have 2, and among all of these values 8 has the highest length of the increasing subsequence. So answer would be 4, which actually is the correct answer, right? 2, 5, 7, and 8. Answer is 4. Now, what we are doing when we are iterating through this thing at whatever element we are at, we have to go to the left, and the time complexity basically is O of n square, because first we have our main iteration through all of the elements and our second iteration when we have our element and we are going to the left, finding the biggest subsequence if this current element were to be taken as the last element. So the time complexity is O of n square, which is not very good, but it works. At least we have something we can hope for, something that works, right? So that is good. Now we are going to write code for this thing. What is this? Longest in increasing sub sequence dot cpp, and basic things. Yep, and our function name would be, it would return an integer and find longest sub. It will take in a vector of integers called a. That is all that it would take in, and vector is nothing. What we have is a vector, not a vector. And now here we will create a vector integer called response of size a, of size a. A is fine. And default value for everything is 1. No matching constructor. Default, this is how you give a default value to a vector. No matching Hmm. Of course, shit. Yeah. If int n equals a dot size, and we can here use it. Makes so much sense. If I equals 0, I less than n, and I plus plus. For a given number, we would have to iterate through the left, right? We would have to iterate through the left. So for int j equals I minus 1 and j greater than equal to 0 and j minus minus, we would iterate through the left, and if aj is strictly smaller than ai, then we can consider this might be answer to our thing. Res I equals maximum of the current value of res I, the current value of res I, whatever it is, or res I plus the current value of res I, or 1 plus whatever the value there is, aj. So that is cool, and at the end we could just return res No, we have to have a maximum variable. Maximum, let's say maximum our answer is 1, and whenever we find answer for a particular thing, we would update our maximum using the maximum variable, either the maximum thing or whatever the answer was for the current thing that we calculated, and then return an x, which is cool. And then we can here give some input to our thing a, which has a bunch of elements, which are these. Wait, okay, this will be very cool if I can do this. Vi, this thing, this is a Vim thing, and here inside this percent s every space. No, 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 shit. Okay, shit, it's selected by line. It's selected by line. Shit, I do not want to select by line. Percent s space percent s space. It is selecting by line, which is not good. Okay. What I want to do is replace every space in this thing with a comma, which would be cool. But if I were to do that, every space that is here and which is here would also be replaced, which I could just do a like bad thing and remove these spaces, like this. And now try to do my thing. Replace every space with a comma. Didn't work because let's do this again. Replace every space, yes, with a literal comma. Okay, a literal space. How do you say? A literal. Replace every space with a comma. Do this globally. Okay, something is wrong in this space. Yep, I have selected all the spaces. And what do I have to do? Replace whenever I see a 6 with 5. This thing also doesn't work. Trailing characters. Hmm. Oh, okay, I could do F space replace with comma. Do this like 5 times. Right. Replace with comma. Replace with comma. Yep. Now we are cool. We have our vector up and running. Now what we would like to do is see out, find longest subsequence on this vector A. Output the answer. It should be equal to 4. Let's see. Clang dot slash out. Okay, we did this for the wrong thing. Clang plus plus longest increasing subsequence. Run the thing, and answer turns out to be 8 somehow, which is horrible. 8 is not even close. Okay, we went wrong at some place. Initially, the answer for everything is 1. And then we are going to the left and seeing if this current number that we are on at the left, if that number is smaller than the current I number that we are at. If it is, then update our res I equal to, it should be equal to maximum of res I or 1 plus aj. Aj is not the thing. Res is the thing. Now run it And the answer turns out to be 4, which is cool. And if we were to add a few terms here, like 9, answer would be 5 now, which it is. So that is cool. 5 is cool. And before moving on, I would like to extremely see how can I convert all of these commas in this range as the substitute command. Call it on all the commas and substitute them with a space. That's it. Uh-huh. I would like to see how to use Vim. In Vim, when in Vim, when I have selected some area, and then when I press the command symbol, which is semicolon, which is colon, then I see this thing at the bottom. When I have selected something, I see this thing at the bottom, which is this. Then I see comma this space this at at the command line, and that shows that select the last range that I selected and performs whatever command I give in that range. And I would like to replace all of the comma in that range to periods. How do I do that? Let's see, how do I do that? Excellent. When you visually select something, I do see this. Okay, but this thing is not working. This thing is not working. If this thing is not working, okay, if I have something like this, let's say text thing 1 comma 2 comma 3, and okay, we can do better. We can do control A, G control A. Okay, G control A. Okay, that does not actually work. G control A kind of works. Okay, now we can select this thing, and here substitute every comma with a dot globally. This is the same thing that has been. Okay, we do not use a percentage sign, it seems. Then what is the percentage for? Shit, it doesn't actually work now. Okay, so what is the percentage for? In this range, we are going to change every comma, substitute comma with a period globally in the whole thing. That's what we have. And what we had initially was this thing, uh, substitute every period, okay, a literal period in this thing with a space globally. This is what we had. Vim is actually cool. Vim is actually cool. Substitute every space, but not at the start. Yes, at the start also we have some space. So remove that and substitute every space in here with a comma globally, which is cool. And globally means on the whole line, not just the first time you see that character in that line. That is cool. That is just cool. Vim thing. That is a Vim thing. And now let length k denote the length of the longest increasing subsequence that ends at position k. That ends at position k. Thus, if we calculate all values of length k where k is between 0 and n minus 1, we will find out the length of the longest increasing subsequence. For example, the value of the function for the above arrays are as follows, which is correct, right? Which is what we calculated if we were to output our array, which we can using this template. Before returning, we would just see out this and lang longest see out, right? We see 1 1 2 1 3 2 4 2 5 1 1 2 1 3 2 4 2 5 because we went, yeah, 5 because we have a new extra element in our thing. This is cool. This is cool. For example, length 6 equals 4. 6 equals 4 because if we were to take 8 as our last element, then the longest subsequence that ends at 8 is 2 5 7 8, and its length is 4. So that is cool. To calculate, yep, we will iterate from 0 till n and then from 0 till k. So that is time complexity is n square, which is bad. Yep, this code works and n square time because it consists of two nested loops. However, it is possible to implement the dynamic programming calculation more efficiently in nlog n. Can you find a way to do this? I think we can do this because it is increasing. It does not matter if I have a smaller number multiple number of times. So I think we can use a map. We can use a map and use lower bound and use lower bound to get to a nice place and then iterate through all the numbers which could be added in this. Or maybe we could use a pair in which the first number would indicate which number we are choosing and the second would indicate which we are not choosing. Or the thing is, yeah, that would be true. We could use a pair and add our pair into a set and use binary search on that set. Now, paths in a grid, and then we would have the main boss, knapsack. Knapsack is a set of problems. Knapsack problems S. It is a set of problems, which is cool. Now, if we have something like this, paths in a grid, our next problem is to find a path from upper left corner to the lower right corner of an n by n grid such that we only move down and right. Each square contains a positive integer and the path should be constructed so that the sum of the value along the path is as large as possible. So that it means we are here at the start at this block on the top left and we have to get to this block at the top bottom right, and the path that we choose to get to this point, whatever numbers we have to go through on that path, their sum has to be maximum and our only motion is downwards or towards the right. And what would we see if we were to copy paste this thing in Excalibur? That is that works. That works. That is not very bad. So if we start from anything, let's say we are here, we could either go down or right. Those are the only possible things we could do at any given index. And that is cool. And we have to find the path which has the maximum sum. So we could start iterating from this for every number that we are at, I could ask two questions. I could get to this number either from here or from here, and then I could choose what would be the answer if we were finding the maximum sum path for this thing, whatever it is, and for this thing. And to get to this thing, I would choose the one which is greater among the two, and that would be the answer for this. And I could do the same thing for 8, and I can keep doing this from the start. At the start, I think a greedy approach would not be good. A greedy approach would not be good. I could ask myself, at when I'm at 3, the maximum sum path would be 3 because that is the only way I could get to 3. When I'm at 7, I could only have gotten to 7 from this 3. So answer for this block would be 10. For this block would be the sum of these three numbers, which is 19. And for this block, the answer would be the sum of these four numbers, which is 21. And the answer for this block would be 28. That is 21 plus 7. And then for 3, the only way I could have gotten to this 9 block is from 3. So the answer for 9 is 3 plus 9, which is 12. Then we have something interesting. For 8, either I could have chosen this path or this path to get to 8. And if I were to come from here, I would have sum equal to 12. Sum of 3 and 9 is 12. But if I were to come from here, the sum would be 10, which is smaller than 12. Therefore, I will come from here to 8 and then add to 12 the value of 8, the sum for 8, which is 20. So the answer for 8th would be 20, and do the same thing for all of the blocks till we get to 8, and whatever the answer is at the last block, that would be our answer for the whole thing, which is cool. And now moving on, this is the actual answer for this part, and we can actually write a program right now which should take a matrix like this. And I would also like to see, there is a thing called a matrix, like literally a matrix, which has been provided to us by standard library, which we could use. But before that, uh, max sum path grid, that is a right name. Now, this will return an integer, max sum path, and it takes in a vector, which is a vector of integer. We will call it grid. And let's say int, nope, we will create internally a vector of int, or maybe long would be good because some could get very big, and response. And the size of this thing would be int n equals, we are supposing that our grid is rectangular. n rows, and each row would have a vector of long of size n. We have ourselves a rectangular grid, and at the end we would return from this response answer n minus 1 bracket n minus 1 because n is 0 index. Now for int I equals 0, I less than n, I plus plus, and then internally for int j equals 0, j less than n, and j plus plus. What we have to ask is if it is possible, delta. Yes, shape. Okay, I saw this at some place. We can use this thing. A tube, a pair of integers which would contain delta, which means the moves, possible moves, which are, there are only two. in this case, there are only two possible moves, which are one is, and I am writing the moves which I could use to get to a block. So to get to a block, either I came from above, which is represented by -1 and 0, or I came from the left, which is represented by 0 and -1. -1, 0 just means making a move above, and 0 and -1 means making a move to the left. Why? Because when I remove whatever the coordinates of this thing are, whenever I remove 0 and -1, 0 from the height, from the number of row, and 1 from the number of column. The column here is column number 1. This one on the left is column number 0. This is column number 1. If I remove 1, I will get to column number 1, column number 0. That is it. And now for auto dx dy, I don't think we have to be this elegant in this way, but yeah, we can do this. And delta, you'd get, if the new ones that we will get to, or di and dj would be better names, if di plus I. Now we have to see if the ones that we are at, if they are like not outside the grid. If di plus I greater than equal to 0, and dj plus j is also greater than equal to 0. And I think this is more confusing, and instead we could simply use I minus 1, and yeah, if I minus 1 is greater than 0, that is I can move one row up, and the answer for this thing would be res. Let's say I went to res I j from above, it would be answer, or grid, it would be res I minus 1 and j. And then if j minus 1, if I can move to the left, equals 0, then res I j equals res I and j minus 1, or we have to take the maximum of the two. Initially it is 0. Initially it is 0. We have to take the maximum of the two, comma, res I and j, maximum of these two. And when I have made both of my moves, res I j plus equals value in the grid, which is grid I j. Undeclared identifier j, which does make sense. Right. And that is cool, and that should return the right thing, the sum. Now we have to put our grid into this, and our grid looks like this. It's cool. We can do this, work this out in Vim. This is what we have, and this is going to be a vector of integers called grid. Copy this, put this here, and what we want to do in this range is put every space, replace, substitute every space with a comma on the whole line. Now half of the stuff is done, and What I need to do now is put a opening bracket here. Okay, shit, a macro, shit. We can use a macro. We can use a macro to do this whole thing. Q1, recording in register number 1. And shit, this is called macro pressure. What you do here is this thing perform the operation on one line. After doing this, exit, go to the back, this and a comma. And at the end, you go to the start. Shit, shit, I messed up. I messed up. I messed up my macro. Shit, I messed up the macro. I messed up the macro. I messed up the macro. Shit, I will have to do this again. So what I'm trying to do is I will do this operation on a single line and I can record every keystroke and I can repeat it again on all the lines and tell NeoVim to repeat this operation 5 times or however number of lines there are. So Q, I have pressed Q, you can see here, and 1. Now record into register 1 every keystroke, and it is this. Command S, substitute every space with a comma on the whole line, then go to the start of the line, put a opening bracket there, go to the end of the line, put a closing bracket there, and put a space. Exit out, go to the bottom, and get to the start of the line. And now Q, our macro has been recorded, and I have 4 lines, so I can do 4. I guess it is control 1. Shit, shit. It does not work. It does not work. Uh, how do I? Okay, I think I should have recorded it in some other register. Okay, let's do this again. And now recording in register A. Select the whole line. Select the whole line. Substitute every space with a comma on the whole line. Right. Exit out of select visual mode. Go into insert mode. Add a closing bracket. Go to the end. Add a ending bracket. And the phone is somehow running out of battery, even though it is on charge. And go to the end, put a comma, get out, go to the next line, get to the start, and close the macro. And now 4 control A. Okay, shit. Okay, how do I start a macro? How do I start a macro in NVIM after recording it? Q, this thing, okay. Okay, at the rate followed by the name of the macro. 4 times at the rate A. See, that is magic. That is New Wing magic. That is New Wing magic. And my phone is running out of battery, which is horrible. Why is that the case? It shouldn't be doing that. Okay, now it is cool. Now it is cool. And that is New Wing magic. Yup. Good morning. Did you see this magical thing which happened? Like, look at this. I have this thing and I want to convert all of these lines into something like this. Put commas between every number, put curly braces to the left and to the right, and put a comma at the end of everything. We have a macro in NeoVim like this, which does the whole thing. I recorded a macro and And recording a macro means recording every keystroke that I made to convert something like this into something like this. And then I replayed the whole thing, which is just cool, very cool. Control A, right? This is very cool. Now we have our grid and we can see out. Response is max sum facts for the grid. And yep, we are doing dynamic programming. I want to get like I want to get to know knapsack kind of problems. And that is the next thing, next topic that we will get to. Knapsack is pretty cool. Clang, nope, not the longest increasing subsequence. What are the things? Longest increase, max sum path, max. That reminds me of Max Verstappen. 67 is the answer. 67 is the correct answer. That is cool. That is NeoVim. It is not an IDE. It is not an IDE. NeoVim is not IDE. It is just a simple text editor. And let me show you something. So let's say I have a vector which I want to print, right? And I can do something like OS stream and operator overwrite this operator which will take OS stream reference called OS, and it will take a vector of integers called A and do some logic and return OS stream for A0, something like that. Like, mm, and something like that. I could write this every time. Like this is toys play. Like this is just for an example. This is not the right code because I'm only printing the first element of my vector. But if I wanted to print my vector, this is how I would do it. But instead, we are using newer. So I can do this space. The whole thing is here. This thing has overwritten this put into character for when I'm trying to put a vector of any type t into the output stream. And how does this voodoo magic happen? This happens because of this. I have a file in my NeoVim configuration which has that code which I just printed. This thing, print vector. This is the thing that was printed there. And I have in my configuration a file named snippets.lua. Lua is a programming language which you can use to configure your NeoVim. And in here, there is a bunch of stuff. But the main thing is this thing. Local, here I am going to the file print vector.cpp, which has the snippet which prints vector, and I am just taking it and I am telling NeoVim that whenever I am in normal mode, this thing, whenever I am in normal mode and I press leader POV, leader is space. Whenever I press space POV, run this function, and this function takes in that snippet which prints a vector and prints it at my current cursor position. This is NeoVim stuff. NeoVim is pretty cool. And I have other snippets also. I have other snippets, boilerplate for my CP thing, boilerplate for solving CSE problems, the Diophantine equation boilerplate, which we derived the other day, lead code boilerplate, and yeah, index sort if I ever want to index sort something. And primes, it has code for HPF, the sieve algorithm. Yeah. NeoVim is cool. NeoVim is cool. NeoVim is actually pretty cool. A Mac, I'm using a Mac. And yes, it is very cool. Yeah, you can switch. You can switch. And but the thing is, it is very hard to get used to. It took me a few months to even just because because it is very different, right? Because you are very used to using mouse, and when you are using this, you everything is on the keyboard. And yes, I am using Mac, and you can go here. The Prime Agent Mac, he explains stuff. You can watch his video, and you do not have to just switch from VS Code to NeoVim. There are two things. There is NeoVim Motions, which you could use, which is just this navigation, which is just this navigation thing, mm, which I can use to edit my text. And then there is the Vim editor, which lets me do stuff like this, crazy stuff like this, right? So you can use this navigation Vim with Vim motions inside VS Code right now. There must be a plugin which you can use, and you can practice using all of these things, and then you can switch. The configuration is messy. Learning how to configure NeoVim is actually pretty hard. There's this guy, uh, VHYROO, something like that, or understanding NeoVim. Yep. You can also watch this playlist. This is the one that I watched, and I had to watch this 3 times to understand how NeoVim works internally, how to configure my NeoVim. Yeah. But this is very rewarding. This is actually very rewarding. M1. I am using M1 Air to do my stuff, and yeah, and I would highly recommend to switch over to NeoVim, because even though the learning curve is steep at the start, but the rewarding part is very rewarding because I can do crazy stuff like this, which is crazy. And let's say I want to solve a Diophantine equation. I can press, you can look here, everything I press will be here. This 20 means I just pressed space, right? And space DIO, and the whole code to find the solution to a Diophantine equation is here. Extended Euclid method, extended GCD, find solution for a Diophantine equation. Everything is here. That is very, very cool. And it is very rewarding. Yeah, very cool. And yep, moving on, we did write a function which gives us the right answer for this thing, which is max sum path dot cpp. Here, this is the function. Will delete. This is the function, and we were getting the right answer for this thing, which is 67. 67 is the correct answer. And yes, we are asking the same question. Either we could have gotten to this thing from above. For any square, we could have gotten to that square from above or from the left. And whichever is the maximum, pick that one and add the value of the current square to that thing, to the current response for this square. The recursive formula is based on the observation that a path that ends at square xy can come either from square which is to the left, y x minus 1, or square x minus 1, or square y minus 1 x, which is the square above. Thus, we select the direction that maximizes the sum. We assume that this thing is 0 if y equals 0 or x equal to 0. The sum would be 0 because no such path exists. We assume that this thing is 0 if one of them is 0 because no such. So the recursive formula also works when y equals 1 and x equals 1. Why would this be 0? Because to get to that square, you have to get to the square, right? Yeah. I could never get to this square, but the answer here would be 3 because I'm at this square at this point. That's cool. I use M3 Pro. Shit. I don't know what's the difference between M1 and M3 because I barely see any difference, but price gap is too much. Apple is fooling me, maybe. Yeah. What I've heard is that the initial gap between all the Intel laptops and the Mac M1 was very huge, but since the gap between M1 and the other models is not that high. But yeah, I do see a performance difference. I have lower RAM and lower number of cores. I recently started doing SQL and there are so many functions and stuff. I barely remember things. Yep. So I guess practice would be cool. SQL is cool. SQL is cool. And yeah, SQL is actually pretty cool because if you know SQL, then you do not have to use ORMs, which is object relational mapping, because there is the JSON representation of data in which you have key value pairs, and then there is the SQL representation in which you have to select from tables and do everything. People like the JSON representation, and so to create a link and to let people access the SQL more low level representation using a JSON representation, we use an ORM in the middle, or maybe I'm messing up. I think ORM is not the term. One of the examples is Prisma. Yeah, Prisma is an ORM. Yeah, ORM is the term. So ORM are the bridges which through which you will get a unified interface, and behind the scene you could be using SQL or anything, MongoDB, anything you like. So that is an ORM which you could use. But if you understand SQL, it is pretty good. I've used MongoDB, but it is so useless. Shit. MongoDB to me seems to be a noob thing, right? Because yeah, because it seems to be very easy, and if you are only using MongoDB and you do not know how to use SQL, it seems like you are missing a lot, and that is bad. You should have low level understanding. Like if you are not coding in assembly every day, but at least you should know how assembly works. That would be pretty nice. And now getting back to the thing, because the thing that I want to get back to is knapsack. Yes. I will read about knapsack from CP CP algorithms, navigation. Please consider supporting them. Add free volunteer them. And dynamic programming, knapsack. This is the article that we will go through in just a minute. So yeah, thus we select the direction that maximizes the sum using this thing, and this thing does not make sense. What does this mean? Because no such path exists. Since the function sum has two parameters, the dynamic programming array also has two dimensions. Yep, dynamic programming array, that is a nice term. The data structure in which we are storing all of our solutions. And this is essentially what we did. That is cool. But this one is error prone. I mean, there is obvious bug. No, there is no obvious bug because this thing, we are not starting with 0, so we are not going till -0. That is cool. And the time complexity is n square, which is bad. And now on to knapsack. Firebase is pretty cool. I haven't used Firebase. I would have to use Firebase. Yes. Yeah, I have to do a lot of things in web development. I have not done a lot of things. I have to do things in web development. And now, knapsack. The term knapsack, German, uh, Kugelstuhl. The term knapsack refers to problems where a set of objects is given and subsets with some properties have to be found. Knapsack problems can often be solved using dynamic programming. You have been given a set of objects and you want to find a subset with a certain property, and we can use solve this using dynamic programming. In this section, we focus on the following problem. Given a list of weights, this determine all sums that can be constructed using the weights. Okay, shit. All sums that could be constructed using the weights. Okay, if these are our weights, then there are, what is the possible number of subsets? 2 power 4, 16 is the possible number of subsets, and we could iterate through every subset and find the sums and use a Boolean array or even a set. And whenever we see a new sum, we can just push it to our set, or we can just push it anyway because it is a set, it will not appear twice. For example, if the weights are like this, then these are the possibilities. In this case, all sums between 0 till 12 are possible, except 2 and 10. We could never get to 2 and we could never get to 10. Okay, for example, the sum 7 is possible because we can select 331, that is 7. To solve the problem, we focus on subproblems where we only use the first k weights to construct sums. Let possible x k equals true if we could reach a sum of x using k. Okay, if we could construct a sum of x using k first k weights, first k weights, first. Okay, a subset of the first k weights, I guess, and otherwise equals false. The value of the function can be recursively calculated as follows. Which means, right, to get to a sum of x and I have k elements, then I'm remove the element with the, like, to the right, from the right, and I see after removing it I will have k minus 1 elements, and either I did use this element or I didn't use this element. I am taking it so. This would be true if I did use this element and I got a sum of x minus wk, the kth weight, or if I didn't use it and I want to find a sum of k, a sum of x. But we are going from top to bottom. What about 8? If we have 8, and that is cool because if I am using this thing, then 8 would be reduced by that much amount and it will become smaller, right? It will fit, right? That makes sense. Okay, I will not read any further and I will try to code this thing, like just this thing, and try Gen AI, then web dev, because Gen AI will replace everything. Shit. Here in US, Web3 is preferable than Web2. Yes, I have thought about Web3 and I've purchased a course. Yep, purchased a course on Web3 which I will be taking next year after I get really good at competitive programming. And yeah, generative AI I will have to get into by help from Andre Karpathy. And now this thing, we would like to code this thing. And or not this thing, we can make a folder called knapsack. Go into that folder and clear. The name of the file will be find ways find sums.cpp. And okay, what is this going to have? This will have a function. What do I want in return? I would like to have this array of numbers which I can get as a sum. So vector integer will be returned find sums, and this thing will take a vector. Yep, vector. This will this thing will take a vector, a reference to a vector, and yeah, let's call it nums, and a target int x, and also limit, because in this vector I'm not using all of the elements, I'm using elements till some particular number, right? And this function will return true or false. My bad. We would have a wrapper function around this. We'll have a wrapper function around this. Find sums is possible, and this one will be called find sums. And what will this take? This will take a vector, simply a vector, and it will return the answer. Rest or vector integer rest, and at the end return rest. Okay, and the possible sums that I could reach is the maximum sum is the sum when I'm using all of the elements in nums. And I think there should be a C++ function which I could use to find the sum of all of the numbers. I could implement a loop manually, but I think there should be a function. Uh, C++ function to find sum of vector and elements. Accumulate, 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 accumulate. Some vector, okay. Accumulate takes an iterator to the beginning, an iterator to the end, initial value of the sum. 0 for numeric type. Okay. And this will return the number. So, and max Verstappen range is going to be accumulate nums dot begin and nums dot end. It start with 0. That is cool. For int I equals 0, I less than equal to range. Range is the maximum sum that I can get and I will get, and I plus plus. Now, is if is possible using nums. The right limit initially is nums dot size, which you can store in n equals nums dot size, and n and the sum is I. If that is true, if that is true, then this dot pushback I. Now we need to implement this thing, right? And the approach is recursive. Return is possible for nums, right minus one, right minus one. I have reduced the size, right, right. Okay, and I also need to have base cases. This or is possible nums, right minus one, and x minus the number that is on the right thing. Nums, right, and this is going to give me error. This is going to give me error because I have to do n minus one here, right? And what is going to be my base case? Base case is if the sum of these elements, no, no, base case is if x equals, if not x, then I've already reached the sum, return 0, return true. That would be the only thing, right? That would be the only thing. That would be the only thing. And this is going to create a lot of branches because look at this. Inside a function, I'm calling the same function twice. Time complexity is going to be 2 power n because at every layer, I am making 2 more recursive calls, which is bad, which is very bad. So if I could avoid this, it would be preferable. My nums is not changing. So what I need to know is right and x. So I can create a map from pair of integers to a Boolean value and call it memo. And now if memo bracket right comma x, if I have it, then return memo right comma x. Else if I don't, then response is this thing. And before returning memo right comma x equals response, whatever the value is for this thing, and response. Okay, so we also have memoization now and cool. Return response. Right. Cool. Vector integer are possible set of numbers. Nums is that is bad. Nums is 1335. 1335. And answer response is going to be find sums for nums. Yep, find sums for nums. And now I would like to print this vector, but I cannot do this directly. So the same thing. Shit. Uh, uh, Now I can print because we have this overriding thing. Shit, I was in the wrong thing. Okay. Blank plus plus find sums. Okay, and run it, and hopefully we see every number from 1 till 12, 12 included, except 2 and 10. Or maybe we might see a segmentation fault. CD, knapsack, N, find some slot, CVP. Okay. Uh, yeah, this should be cool. This should be working. Okay, what are we doing wrong? We are getting a segmentation fault because we might be calling this function a lot of times. 2 power 5 is, should we are actually calling this function a lot of times, I guess. Let's reduce our sample size here. Let's have only 2 numbers. Then our answer should be 0, 1, 6, 5. That should be our answer. That should be ideally our answer. But we never know. We never know. We just never know. Okay, so we are getting some segmentation faulting. And to narrow down, we start from here. Create a vector res called res just due to some response. It is going to be our response, so we are calling it a res. And then n has the size, this thing, and range has the sum of all of the elements from starting till the end of our numbers vector. And initially, the thing that we are starting our counter with is 0. And then we have our iterator starting from 0 till range equal to range. And then we are checking, is it possible to get to nums through nums using the things that have been provided in nums to get to the sum I. If it is possible, then push back I into res, right? And then at the end, return res. And we are doing this for every number from 0 till range. And the number will go up till range. It will be equal to range at some point. And in this is possible function, we are taking in all of these parameters and then we are checking if, okay, I can remove this memoization part. Now, if not x, if x, the sum that I'm trying to get to, if it is 0, then true, I can always get to a sum of 0 by not choosing any elements. And Boolean response. Is it possible when I use, wait, I am never returning false. I am never returning false. I am never returning false, which is bad. Okay, shit. If right lower than 0, that should have been the second test case, second base case. Okay, now we are actually cool. Now we are actually cool. I could use 3, 3, find some, and hopefully we do see the correct answer. We have every number from 0 till 12, but we do not have 2, 2, which should have been here, and we do not have 10, which should have been here, which is correct to this thing. So this works. This works. We implemented this thing, but let's say we increase our size of sets to just, I have only increased 3 numbers. Let's see how long it takes now. Okay, that was not very long. Let's say, right. Okay, that was a bit bad. Yeah. Let's say we have this many elements now. How much time does it take now? It is taking quite a bit of time because it is going through everything. Yep, it did took some time. And let's say we are adding now bigger numbers. Now it is going to be very bad. It is doing its thing, whatever it is supposed to do, whatever we have written, and it is taking a lot of time because there are a lot of recursive calling going on, and we do not want that to happen. So we will have a pair of integers, int, and its value is going to be an integer, and we will call it memo. And before returning, we would check if memo for right and x has already been found, then return memo for right and x. And if we don't have it, then put it into the memory. Right and x equals to response, whatever it is. We still do not have this answer. It was still running. Now let's see. Does it work now? Is it any faster? It is not very fast. Okay. Okay, it is. This one is also still going. I think this is because of these numbers. These numbers are very big. But this should be, yeah, this should still be faster than the normal implementation, which we can check. Let's say this thing, right? This is our implementation using memoization, and it is seems to be working. It is doing its thing. It is still taking a lot of time. This is very slow. Very slow. Shit, this is slow. It does work. It is correct, but it is very slow. It is very, very slow. If I reduce a few more numbers, it is slow. Shit, it is very, very slow. Let's say I remove all of these numbers. F or D, D, T, this. Yep. Let's see, we do that, and now we recompile, and now it is working much better. Let's see, we remove a bunch of numbers. This should work. This should, okay, it is taking a lot of time. It is, now we have the output. Yeah, but it's still, it is very slow, and we would like to optimize this quite a bit. And we will see how we can do that. Shit, now it is better. And I was not in the center, it seems. Yep, now it is cool. So yeah, we have implemented this thing, but this is very slow. This is very slow because just look at this. This function is calling itself twice, which is not very good. The formula is based on the fact that we can either use or not use the weight wk. Yep. In this case, we did use our weight wk, and in this case, we didn't use our weight wk. In the sum, if we use wk, the remaining task is to form the sum x minus wk, form the sum x minus wk using k minus 1 elements, using the first k minus 1 weights. And if we do not use wk, the remaining task is to form the sum x using the first k minus weights. As the base case is this. When the set is empty, when I have used all of the elements in the set, if x equals true, then true. If x is not equal to 0 after using all of the elements, then false. That is cool. That is correct. Because if no weights are used, we can only form the sum 0. Yes, when because the size of our set is 0, so we can only form the sum 0. That makes sense. And okay, just looking at this base case again, I start with a bunch of numbers, let's say, which in this case are 1, 3, and 3 and 5. 1, 3, 3, and 5. The minimum sum I could get is 0, which I'm guaranteed to get when I use a empty subset from this thing, when I'm not using anything. I guess empty is like this, empty is like this. And the maximum sum I could get, wait, yep, now this is better. The minimum I could get is 1. No, these are the numbers that I have at my disposal. The minimum sum I could get is 0, and the maximum I could get would be the sum of all of these, which is 12, when I am using all of these. So for every number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. For every number in this range, this is 9. I have to ask, can I get this sum using these elements? And the function I am using is possible. Is it possible to use the first 4 elements to get to a sum of, let's say, we begin with 1, to get to a sum of 1? Is it possible using the first 4 elements? Well, we don't know. We don't know. So what we will do is, let's say we maybe did use 5 and maybe we didn't use 5. This is going to make 2 recursive calls. This is going to call P3 and -4 and P3 and 1. What did we do? We in both case switched our 4 to 3. That is, we removed our 5. And in one of these cases, we did use the 5 in our quest to get to a sum of 1, and in the other case, we didn't use it. Now we are asking the same question again. Can I get to a sum of -4 using the first 3 elements? And I think there is no point in pursuing this further. Like, this is bad, this is not going to work, because I can never get to a sum of -4 using a set of positive numbers. So that is bad, but we can move further here. This is going to call 2 recursive calls, 2, and again, the third number here is 3. In one case, I did use the 3, and now my target sum is -2. And in the other, I didn't use, and my target sum is still 1. And this thing will be caught beforehand, and we will not pursue this any further. And actually, I can write this into the code. If at any point, if just this, if this thing, if x at any point is lower than 0, return false. So if this thing becomes lower than 0 at any point, return false. So we will not pursue this further, but we can pursue this one. This will call p twice using 1, and the second element is also equal to 3 right here. This is also 3. So in one case, we did use our 3, and in the other, we didn't. P using the 1, and this thing is caught, and we will not pursue this further because we cannot get to a sum of -2. And this thing, in one case, we did use 1, and our element number 1 is 1. So in one case, we did use 1, and we got to this. So now we need a sum of 0 using 0 elements, and in the other case, we didn't use 1. So from 0 elements, we need a sum of 1. And this thing, now we are already at the end of our set, and we have used up all of the elements in our set from our set, and we need a sum of 1. So nah, this is not going to work. But this thing, we have used all of the elements from our set, and the sum that we need is 0, which is possible. So this thing is going to return true, and this true is going to propagate through this chain up till this function, and this function will at the end return true, which is cool. So we know that we can get to a sum of 1 using the first 4 elements, and then we are going to do the same thing for every element from 0 till 12. We can actually go till lower the range, and at the end this dot push back range, because we know we can get to range. And here we can start with 0 because we know we can get a sum of 0. That is cool. Now moving on to this thing. Yep. The following table shows all values of the function for this. Yep. The X symbol indicates the true values. To get to a sum of 0, I didn't use this. This represents the first 4 numbers. To get to a sum of 4, I why is there no x? What does x mean? The following table shows all the values of the function for weights this. Yep, from 0 till 12, the symbol x indicates true values. Okay, makes sense. Okay, makes sense. Using the first 0 elements, I was able to get to a sum of 0. Using the first 1 elements, I was able to get to a sum of 0, and so on. For using all the elements, I was able to get to a sum of 0. But I was unable to get to a sum of 1 using 0 elements. But I was able to get to a sum of 1 using 1 element, 2 elements, 3 elements, and 4 elements from the start. And I was not able to get a sum of 2 using any number of elements. So there is no x here. I was able to get to a sum of 3 using the first 2 elements, and that is what it represents, this whole thing. And we move forward. Right. And yep, what do we have? After calculating those values, possible x and n. X is this value, n is this value. No shit, I messed up. Yes, I was correct. X is my bad, this value, and n is the number of elements we are using from our set. Tells us whether we can construct a sum x using all the weights. Right. With let W denote the total sum of the weights. Yes. The following O NW time dynamic programming solution corresponds to recursive function. And we could have used iterative solution also. Okay, let's try to implement this in iterative way. I No, this is not iterative. This is not iterative. Actually, possible 0 0. Yep, this represents this thing, possible 0 0. And okay, it is possible to get to a sum of 0 using the 0 elements. It is true. And then we are iterating through k. K goes up till n, and k is our number of elements we are using from the start. Number of elements we are using from the start. For int x equals 0 till x less than equal to weight. When we are using one elements from the start, we will see can I get to a sum of 0 and so on till w, and then we would be using two elements from the start and we would ask the same question. And if x minus w k is greater than equal to 0, x is the current sum that we want to reach, and if I subtract that from the last number, if that thing is still 0, if I have something there, then I would ask the question if the sum that I want is still positive or at least not negative, that is greater than equal to 0, then is it possible to reach that sum using the first k elements? Its value is going to be equal to or possible value, and the possibility to reach x minus the last number using the first k minus 1 elements. If possible, xk, otherwise, okay, shit, this makes sense. This thing initially is equal to 0. You do not have to use this sign. You do not have to use this sign, right? This is a bit confusing, but it is fine. If this thing returns true, then this will become true. And if this returns false, this will be false because this initially is false and we are taking OR of that thing. And here we have possibility, we are checking again. Here we are checking if we did use the last element, and here we are checking we just reduced our range but we didn't use the last element. That is what we are checking here. And since we are going from lower till above, this is going to work. And this is actually much better than the recursive approach. Shit, this is actually much better than the recursive approach, this shitty recursive approach. Okay, we are not going to use memoization. Okay, we will have a vector of vector of Boolean values. Possible size is going to be crazy thing. And let's say whatever number we have, we can possible dot assign num size, that is going to be the number of rows in this matrix, and then vector bool, and the number of elements in the size of columns is going to be the same. It is not going to be the same because the first thing represents the maximum sum and the second one represents the size. Okay, so this is not going to be this. Okay, what was the change? Okay, how am I calling possible here? Now this cool, but the thing is, yep, this is cool. This is cool. Yep, there is some mistake, and range is going to be accumulate nums dot begin till nums dot end start with 0 as your sum and get everything, and this first thing is going to be equal to range plus 1. Actually, this all of this should be done in inside here. This will return a vector of integers, find sums, and this will take in a vector of integers called nums. And let's define a vector of integers called res, and at the end we will do something and return res. That is what we do, and we do not need anything like this. We can do all of this here. Int range equals accumulate nums dot nums is spelling wrong, nums dot begin and nums dot end, and our sum starts at a 0. That is what we have. That is what we begin with, right? And possible this go inside and have range plus 1 stuffs vector, vector of not integer, boolean. Yeah, vector of boolean, and size is going to be nums dot size. Cool. And now is the thing, for int I equals 0, 0 is fine, 0 is fine, I less than range, I will represent the range, I plus plus, and this is opposite to the loop that is in the book, but it is fine. Okay, okay, let's make these more meaningful. S means sum. Fi replace with S. S means sum, and that is the sum that we are trying to get to. We go till equal to, and J0 is the number of elements that we are using. We can call it K, and while K lower than the number of stuff, number of elements, yeah, size of that thing, K plus plus. Some of this is bad because of this. Now, given this thing, I would have a few questions, but possible before this. Vector possible, yep. It is possible to get to a sum of 0 using 0 elements, which is crazy. It is possible to get to a sum of 0 using 0 elements. And I would not try to get to a sum of 0. Actually, I wouldn't even go there. Yes, I should not be using this. 1 is where we go. Right. And possible if using this number, I could get to my sum. The last number that I'm at is nums k. I need to ask if s minus nums k is greater than equal to 0. If that is the case, that is after using the kth element, the sum that I want is still greater than equal to 0, then possibility to get to a sum of s using k elements will be equal to the possibility to get to a sum of s minus nums k using the k minus 1 elements. And for our first iteration, we would have k equal to 1 and s equal to 0. K equal to 1 and s equal to 0. And seeing this thing, we would have s equals 0. So no matter what number I reduce, this thing would be false and I would not go here. But then I would have to check this thing, the XOR or of this thing is equal to take these things or with trying to get to a sum of s bus but one less element. Okay, why is this not cool? Okay, this is not cool somehow. Possible is A or take the or of these two things. And this looks noby. This looks better. Shit, I could have used take or shit. Okay, it is too bad. This is too bad. Possibility to get to a sum of k to a sum of s using k minus 1 elements or of these two things. And my phone has again stopped charging due to some reason. Okay, my laptop is out of charge. My phone was charging. Okay, we have this thing. And if at the end this thing is true, then we can push this into our array. But we do not want to push this multiple times. Yep, we do not want to push this some multiple times. Yeah, but we can do just this. When I have checked this, if possible to get to a sum of s using all of the elements, nums dot size minus 1. If it is possible, then restart, push back the current sum, and at the end return sum. Okay, that looks not very elegant, but this thing works. Okay, where am I? Find sums. Shit, seems like I lost the whole thing. Shit, shit. I did actually lost the whole thing. Things happen. No, I do have it. I do have it. But in the wrong place. Okay, my bad. Quit. Find sums. Do I have it? I do have it. That is cool. Clang plus plus. Find sums. Not slash out. And we see nothing. Because of course we are not calling the function. See out. Find sums. Call this on our sums on our nums vector and clang and c slash out and nothing. Zero is the only thing we could get to, which is bad. Which is bad. Shit, which is bad. Zero is the only sum we were able to get. Okay, where does our k begin at? I think the way that we are iterating is wrong. The way that we are going through this is like the order which we are using here is totally wrong. Let's see. We are first iterating through the sums and then we are going through the number of elements. right? The order in which we are going through the number of elements from the first till the point when we are using all of the elements, it is cool, it is correct. But maybe we should iterate through all the sums and through all the number of elements first, and then go through the sums that could be reached using those k elements from the start. If s minus 1, s minus nums k greater than 0, this should have worked, right? For the last k, but this is never equal to the last k due to some reason. Okay, because shit makes sense. Yeah, it does work. It does work. That is cool. It does work. We can check it on some array for which we already know the answer. 1, 1, 3, 5. D till this and 5. Blank dash dash out. And that is wrong, actually. Yep, that is wrong. That is actually wrong. Shit. Okay. So there is a mistake. That is wrong. Okay. If I do this, that is wrong, but S K or with this thing, and if I start iterating from this, should not make any difference. Here, the order of our iteration, if we were to look at this thing, would be something like we are iterating from here, 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 here. No, we are iterating from here, 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 yep. And then from here to here. Uh, we are iterating like this for a given sum S. Check this, check this, check this, check this, check this. And then for a given sum 1, check this, this, this. And then like that. And this thing would be true if here or here. No, that is not the correct thing. This thing would be true if I sub equals to XOR of the current thing with, if I did use this current number that I'm at to get to my sum using k plus 1 elements, would it be possible? We would check if it is possible or not. Yeah, this should be working. Yeah, I think this would not work. This would not work. Yeah, this does not work. Makes sense. Why? Because this does not work, even though we are. Is this whole thing 1? That would be a interesting observation. When we have sum equals to 0, we are going k. This thing is true, we know for sure. But this thing would also be true because our s is 0 and k minus 1. If k were 1, it would be 0 and 0, 0 is true. So this would be true for k equals 1. The same for every other number here. Then we get to 1 and then we get to s equals 1 and k equals 0. That should be false. And this thing equals OR of this thing with this would never run. This would run k equals 0. The number at is okay. Shit, we messed up. We messed up a little bit. We messed up a little bit. K equals 0. Yeah, we messed up a little bit. What is the case when we are not using any elements? Yes, shit. When k equals 0, we are representing it as if we are using the first element, but we are not using the first element. Yep, we are not using the first element, so that is the mistake. Our invariance is wrong. So k equals 0 would mean we are not using any elements. We go from k equals 1 till k equals this thing, and you just do k minus 1 to get to that element, but it is also bad. It is also not really cool. Like it is exactly the same thing. But all of this would be 0. Take its XOR with k minus 1, k minus 1 to get to a sum of 1 using minus 1 elements does not make sense. Here we are doing minus 1, k equals minus 1, using minus 1 elements does not make any sense. Yes, we can start iterating from k minus 1, k equals to 1. Yep, that makes sense. That does not make sense actually. K represents the number of numbers that we are using from the start. So we would start iterating from k equals to 1 because we know when we are using 0 elements, 0 numbers from the start, we would never be able to reach our sum, whatever it is, if it is greater than 0. Right, so we start with k equals to 1. But if we do that, it is fine, it is fine, it is fine. When we do that, it is fine. Now, kth element does not mean anything. K minus 1 element means something. Possible k when I'm using k numbers. Therefore, this thing has to be a little bit bigger, about plus 1 bigger. Yep, yep. Possible k when I'm using k elements, do this. Possible k when I am using k elements, or with possible k when I'm using k elements, and here will come k minus 1. Yeah, that is cool. If I am using k minus 1 elements to get to a sum of s, if yeah, this seems cool. Save. clang plus plus dot slash out. Uncool, very uncool. Shit, that is wrong. Or maybe not. That is correct. Now we are doing the right thing. So this is correct. This is correct. That was the only thing. The translation between k at one point, k represents the number of elements we are using from the start of the array. And if we want to go to the kth element, k is one indexed. So k equals 1 means the first element, and k equals to 0 means no elements at all. That is one thing. But when we are accessing the kth element in nums, we have to do k minus 1 to get to that element. That makes sense. Now it is configured and it does work. So that is cool. And we can move on to the next question. We do not have a question. We have to at least get to this thing. Yeah, so we have implemented this part. However, here is a better implementation that only uses a one-dimensional array possible X that indicates whether we can construct a subset with some X minus 1. Okay, we are not going to look at that implementation. We are going to actually implement it without looking at it. A one-dimensional array. A one-dimensional array. If I'm using k numbers, if my array looks like this, a Boolean, if my vector looks like this, a Boolean vector of range plus 1. All right, and initially, can I get to a sum of 0? I can get to a sum of 0. Possible 0 means I can get to that sum, right? I can get to that sum. That is possible 0. It is true. Okay, then I'm iterating from 0. I do not have to iterate from 0. I can start iterating from 1. And okay, when I'm using k numbers, when I'm using k numbers from the start, is it possible to get to a sum like that? It would be, it would be if I could get to any sum, if I could use one of these elements or maybe not use one of these elements and get to a sum that is itself reachable, right? But how would that be? I'm trying to get to a sum of S, and I have knowledge about S from 0 till S minus 1 sums. Right, right. If S minus nums k minus 1, I can start k with 0. If S minus 1 equals nums k minus, if this thing is 0, if this thing is 0, then I can do possible S equals true and break. If I have 2 would be false, right? And 3 would be true. 4 would be true. Shit. Okay, this works. This works. This works. This works. This works. Or maybe not. Shit. It does not work. It does not work. It doesn't work. Why is not 4 true? 4 should have been true because 4, when s equals 4, when s equals 4, I would subtract. Okay, yes, 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 yes. If this minus this, if this minus this greater than or equal to 0, and it is possible to get to that number, nums. Okay, if it is possible to get there and it is greater than or equal to 0, then put this. Cool. That is literally all of the numbers. Okay, so for 4 it was correct. For 5, why is it correct for 2? When s equals, it is possible to get to yeah, shit. But the number that I'm using there, I cannot use the same number twice, makes sense. Yep, shit, I would have to therefore change the order of this whole thing. For int for k equals 1, k k k equals 0 when using the 0th element, and k less than nums dot size and k plus plus s sum equals no. We already know about sum equal to 0, which is true, and right, s smaller than equal to range and s plus plus. It would be possible to get to this sum using the first k elements. If it is possible to get to this sum, if I use the k elements, shit, we would have to look at this. Yes, k started iterating from 1 to this, and if possible, x. How do I know this beforehand? X starts at W. We are going from higher to lower now. Higher to lower. Okay. Till x equals 0. And if I was able to reach a higher value, if I was able to reach a higher sum, if I was able to reach a higher sum, that is x. If possible x, if I can reach the current sum using this many numbers, then put possible The last plus true. Okay. Plus one. Huh? Does that make sense? WK is the weight of the kth number, right? WK is the weight of the kth thing. You're not going to zero. For k equals 1 till n till equal to n, we are iterating from the highest sum that we could reach. So here's the outer loop and goes through k. And so we are iterating in this manner from right to left, then in the second row from right to left, in the third row from right to left, then again right to left, then again right to left, and at every position I am seeing if I have this thing and I add the last number, it should be reachable. So when I put this thing true, everything here becomes true. When I put this thing true, everything here becomes true. Surely there must be another way in which I can iterate from sum equal to 0 to the maximum range. Yes, yes, yes. Yes. The current sum that I'm at would be possible if s minus nums k greater than equal to 0, and it is possible to get to that sum s minus nums k. Shit, this would is yo. This would mess up. This would mess up. Yep, this would mess up. No. Mm, this would actually mess up. This would mess up. Yeah, so we have to go in the opposite direction because this would make every possible sum equal to every possible sum possible. This would make everything true. While s greater than equal to 0, I'll do s minus minus, go back, and if it is possible to reach the current sum, I will extend s. If possible s, if it is possible to reach the current sum, then it is also possible to reach the sum s plus nums k. That is that is what you do. I can make this thing a set, and at the end return a vector of integers using res dot begin and res dot end operators, and here res dot insert s. Nah, I could just make a one loop. I equals less than equal to range I plus plus and possible, and if possible I, then this dot push back I, because I is a vector. I can do that, and here simply return rest. Yes, now this should work, hopefully. And it does work. I have 0 1 except 2, which I do not want. It is correct. I do not have 2, and I do not have 10, but I have every number from 0 to 12, which is the correct answer. So that is cool. That is cool. We know this thing. We know, yeah, we have to just practice dynamic programming, for which we have CSCS problem set, dynamic programming. Okay, I guess we will start doing this from tomorrow, which is going to be cool. Bro, other than CP, do you do any dev stuff? I have tried to do dev stuff. Yeah, I'm not really good at it. I have to do it seriously again. I will do it next year, seriously. Also, can you show your CP31 sheet ones? How do you customize your new M? Do you learn Lua or copy someone else? No, my setup is also cool, custom. I have written it on my own, and I did learn Lua. I had to learn Lua to write my own setup. And for CP31, I have done only this much questions. I had to do more. Right. Yesterday, I was trying to do this question and I struggled a lot. Look at this. Look at this. What is this? It just it does not work. Yeah, but I have done this many questions, and yeah, I have to do these harder questions. It is going to be hard. Yep. Lua. Lua is a very simple language, and you can go to this website, learn X in Y minutes, and there is a summary for every language, and you can go to Lua. And Lua is a very simple language. It would not be very hard to understand how Lua works from this thing. Lua is like actually very simple language. It has only 21 keywords, I think. It has only 21 keywords and it does not have any data types. It has only one data type, which is called a table. I think it must be written at some point. Tables, yep. It is called tables. It has only one data type. It is called tables. That is cool. No, it is the question that I was trying to do. It was related to prefix sums, and using prefix sums to find, it is related to range queries, using prefix sum to find and of numbers in a given certain range, bitwise and of numbers in a given certain range. Yeah, and yes, for Neovim, understanding Neovim, you can watch this thing. You can watch all of these videos. Yeah, I would highly recommend watching this whole playlist. This is very cool. This guy explains Neovim and Lua in a very comprehensive way, and it is very cool. He explains what are LSPs, what is Mason. I do not use Mason. Whenever I have to add a LSP, I manually install the LSP and write the configuration for adding that LSP. What are tree sitters? What is text? What are text objects? So yeah, that is cool. this rule. LSP tree sitters. So watch this thing. I had to watch this 3 times in a span of 2 to 3 months to understand this. And you can watch this thing. I had to watch this also 3 to 4 times, spanning 3 to 4 months to understand. And also this thing, this video in which Primeagen goes and writes his whole Vim RC, new Vim RC from scratch. RC is, what is the full form of RC? C is command, recorded command. RC, full form, recorded command. Uh, config RC, full form, run commands, not recorded, run commands. Yeah, this is what I would recommend. Watch this, this, and yeah, after that, you would also like to write in your Vim, right? So apart from the configuration, you can watch this thing to understand how you can use NeoVim, the abilities that it provides. That is cool. That is what you can do. Like building stuff, like concepts to build the new. Yeah, that is what you will learn by looking at watching those videos. Prefix. Okay. Okay. We have switched. That concept was told by Priyansh Agarwal in a video of prefixes and difference. The same concept. Yep. I used Vim motions, so that is cool. And use till now. I started falling in love after using Vim. Yeah, Vim motions are superior to anything you could use. Vim motions are superior to anything that you could use. And let me show you this thing. Uh, yep, I have added a bunch of snippets which I can just paste wherever I want. Like right now, this thing is giving me error. This function returns a vector and I am trying to print this vector. So what I could do is write a loop manually to go through every element of that vector and print it, or I could paste a snippet. This thing, this thing, this is C++ is a specific thing. This overrides this operator, this put into operator, and now this thing is no longer giving me error. But the main thing that I wanted to show is that I can just print snippets anywhere I want. That is the power that NewVim provides. And the snippets are here. CP, my competitive programming boilerplate. Whenever I start writing code for some new problem, this is what I print, and that is cool. It is like actually cool. Everything is configurable, and that is cool. And that would be the end of today's video. It has been 3 hours and 38 minutes. This was cool. Dynamic programming. Tomorrow we will continue, move forward. And today is also a contest. And I want to perform good. And thank you for